Welcome back. This is lecture 17. So, in the last couple of lectures, we were talking about thermal noise, and we sort of solely focused on thermal noise of resistors, and we saw a couple of ways of analyzing noise when these noisy elements are placed in a network, right? So what we'll do, we'll look into the noise emanating from transistors, because I mean, when you are designing anything in analog or RF, transistors are inevitable, right? So we are going to look at the noise emanating from a transistor, and with the example of a transistor, we'd like to extend the noise theory for a generic two-port network, right? We'll do some simplification in the way. So let's get started. So if you have a transistor, let's take the example of an NMOS transistor, and let's assume this is biased in saturation, right? So if you have an NMOS transistor biased in saturation, the cross section of it kind of looks like this. You have this channel which has carriers, which is electrons, and maybe you have lights near pinch off, right? So this is drain, this is source, this is gate. Okay. So similarly, here you have drain, source, gate, and we understand that there is channel here, right? So now when obviously you have biases between gate and source and drain and source, otherwise there is no channel and there is no pinch off. So the electrons are moving from source to drain, so the current is flowing from drain to source. And now you see that there are these carriers that are moving from drain to source, just like in a resistor, right? Just like in a resistor, we do not ideally you do not expect ideally you would expect this IDS to be, when you have a voltage difference between drain and source, and your transistor is in saturation, you should expect your IDS to be half mu n C ox W by L VGS minus threshold voltage whole squared, again neglecting channel and modulation and so on, right? But just like in case of a resistor, if you actually measure the IDS, you are going to see this plus some I or N, and this IN is noise. Again, this will be just like before. You are going to notice this has, should not use mu because we are using mobility for mu, equal to 0, and you are going to have some standard deviation or variance, right? So you are going to have sigma is not equal to 0, or sigma square is not equal to 0. What we are interested in this part of the lecture is to model, or rather is to understand the effect of this IN, and to see how we can model this IN. Okay. Again, at a very top level perspective, what is the cause of IN? So clearly, when you have electrons in the channel, sometimes because of thermal fluctuations, right? Because of thermal fluctuations, you expect, when you expect IDS current to always cross the junctions between the drain and the channel, or the source and the channel, right? But because of thermal fluctuations in the channel, sometimes few extra carriers can pass over, and that random fluctuations of few extra carriers are essentially thermal noise, which is modeled as IN, right? Note that in case of so if I call this, so IN has, in a MOSFET, IN has two components. One is thermal noise, another is flicker noise. These are the two major components. There are other minor components which are also associated with carriers in a MOSFET, but in this course we will be concentrating on primarily these two major sources of noise, and that is thermal noise and flicker noise. And for today's lecture, we will be concentrating only on thermal noise. Okay, we'll talk about flicker noise later on. Okay, so now just like in a resistor, we had a model to model this thermal noise, which was we could model it as a current source in parallel, or a voltage source in series with a resistance. Similarly, in this case also we can model the noise, and the noise model is the most convenient noise model for a MOSFET. A thermal noise model for a MOSFET is a current source which goes from drain to source, and if I call this IN, the sparse spectral density of IN is 4 kT gamma times Gm. Okay, where gamma is equal to 2/3 for long channel devices for transistors in saturation. Okay, for short channel devices, so again, what's the definition of long channel and short channel? In your mind, it should be like a device where you have pinch off, but there is velocity saturation hasn't yet happened, versus a short channel is where the velocity saturation has happened, and the channel and the charge profile in the channel is not really triangular. If velocity saturation happens and the charge profile becomes triangular, this gamma increases from 2/3 and it goes closer to 1, and some devices have also reported gamma to be greater than 1. Okay, but I mean, for the purpose of this course, we'll stick to gamma equal to 2/3 unless otherwise mentioned. Okay, fine. So now the question is, what is effectively the incremental model of our transistor in the presence of noise? Now note that noise by definition, I mean, is a disturbance, but it's a small disturbance, right? You do not expect the noise to be more than the signal. If the noise is more than the signal, then I mean, you will not be anyhow be able to detect anything. If by chance the noise is more than the signal, then you will have to ensure that you design your device in such a way that the value of the noise is such that it is lower than the signal that you expect. So if you which naturally means that for the analysis purposes, if we can use small signal approximations for signal, we should be able to use small signal approximation for noise, right? So all these noise models of 4 kT gamma Gm and everything in case of a transistor are strictly for small signal analysis. They are not for large signal analysis. Okay, so that is something we should always keep in mind. So if we do a small signal analysis, what will be the noise model for this transistor in saturation? It will essentially be this. So you have gate, you have source, you have drain. This is GM times VGS. If you consider channel length modulation, you are going to have a GDS or an RDS. And if you consider a body effect, you are again going to have GMB, which I'm sure you have encountered in analog circuit courses, but we are neglecting the GMB term so far. In most of the course, we are going to neglect unless otherwise mentioned. But let's not get sidetracked. Let's get back to our noise model. So our noise model will essentially be here. This will be IN. Okay. An important aspect to note is that GDS or RDS do not contribute to thermal noise or any noise for that matter. Okay, the reason being GDS and RDS are not physical resistors, they are model resistors, right? They are a mathematical construct, they are a mathematical model that has been designed to help us analyze a circuit. They are not a physical resistance that is present. Okay, the GDS or the RDS is basically a model of how the channel charge profile changes if you wiggle VDS, right? So it's not a physical resistor. The source of noise in a transistor is through the thermal noise fluctuation in the channel, and that is essentially modeled by this red colored current source IN. Okay, fine. So just like the analysis with resistors, if we have multiple transistors in a network, so let's say I have a network where I have resistors and I have transistors, multiple transistors, and I have capacitors and inductors, and I'm interested in finding out the total output voltage at any particular node. So what would we do? What is the most usual thing that we used to do? We used to find out the noise transfer function from each of these noise sources to the output. So now in the presence of a transistor, we would have some more noise transfer functions. So from each of these current source, we would like to find out the transfer functions from each of these current source to the output. And since all these sources are uncorrelated, right, so I can essentially find out each of their individual transfer functions and multiply that mod of transfer function squared with 4 kT gamma GM for each of these transistors and 4 kTr for each of those resistors, and then add them up, right? By the way, important caveat, when I say transfer function, in this case what I essentially mean for transistors is from current to voltage, right? So essentially we are trying to find out the unit of that transfer ratio. It will be ohms, right? So that is something you'll have to keep in mind. Okay, fine. So now this seems to be a tedious job. There are ways to simplify this job, but the part that we are more interested in is let's say how do we represent the total noise of this network in a compact form so that it is useful to design a system, right? So what do I mean by that? So see, obviously when you have a big network, you can do this analysis and you can find out the total output noise. Just in the way that I have shown you, and there can be ways of simplifying it, right? But from a system designer's perspective, consider this fact. Let's say you are in charge of designing one block. I don't know what block is this, but maybe some block, and your colleague is designing block 2, okay, and you want to interface this block 1 to block 2, okay. So there is some interface between block 1 and block 2. So clearly the design of block 1 and block 2 are not independent of each other, right? Because there might be some input impedance associated with block 2, there might be some output impedance associated with block 1, right? So while designing block 1, you would also need the information of the input side of the block 2, and while designing block 2, you would require the information of the output side of block 1, right? So this is, we know this. But what about noise? What type of information? Let's say I am interested in designing block 1, right? What do I need to ensure so that the output of block 2 with respect to this noise performance is fine? So at least we need to ensure that, let's say there is an input here. Let's say I have an input that is coming out. At the output of block 2, I am going to have some signal. I am going to have some signal. And I am going to have some noise, because everything has some noisy element. I am going to have that signal, I am going to have some noise. Now this output of block 1. Now output of block 2 will take this signal and the noise that is coming out from block 1 and is going to process it and also add its own noise, right? So effectively at the output of block 2, I am going to have the signal, I am going to have the noise of block 1, and I am also going to have a noise of block 2. Correct? So now when I am designing, if I do not have the information of block 2, how much noise the block 2 is going to add to the circuit, then it becomes difficult to design my block 1. For example, if I know that the block 2 noise is significantly large with respect to the signal that block 1 is providing, then I need to ensure that the block 1 has large signal gain, right? So now the question is, how can I represent the noise of block 2 in such a way that is useful to me, that is useful to the designer of block 1, right? If you see the data sheets of various analog circuit blocks or even RF blocks, you are going to see figures like input referred noise, you are going to see figures like noise figure, you are going to see integrated noise, and so on, right? So all of them are essentially trying to capture the information of the entire noise provided by a certain block into one number, right? The benefit of that is it helps the designer of the previous or the subsequent block to design their blocks. If I know what type of noise I am going to encounter from a block that is preceding me or the blocks that is succeeding me, right? So which essentially means that we need to have a way of encompassing the entire noise information, not only at the output side but also to the input side, right? So what we'd like to do is to find out, next job is to find out a compact way of representing the noise of a network. Okay, just like you know that we have Thevenin equivalent, Norton equivalent, and so on to represent a complicated LTI network into a bunch of simple resistors and voltage sources or current sources, right? Similarly, we would like to have a compact way of representing the noise of in a system into a compact format. Okay, so let's consider a generic two-port network and see what are the ways of or let me instead of going for a generic two-port network, let me take the example of a single transistor and show you, and then we'll probably extend it to a generic two-port network, right? So let's do that. So let's say I have a transistor in saturation and it has a noise current IN, and let's say I'm only interested in the output noise current, right? So I'm not showing biasing. It is assumed that things are biased, right? So I'm interested in this I out, and I'm interested in the I out noise, okay? And let's say I have a input source which has a resistance Rs, okay, and I'm going to interface this Rs with this transistor, right? So I'm going to interface this Rs with this transistor. I need to understand what sort of input voltage I should have so that I can get an output which is higher than the noise level. And I'm showing this with the toy example of one transistor. You can assume there are like hundreds of transistors in the network. Okay, so the goal is to essentially can I represent this as, so by the way, this is the network boundary, right? I cannot touch Vi or Rs. The goal is, so you have Vi, Rs, this I cannot touch. The goal is, can I do something, can I represent something in the network boundary in such a way that what is a simplistic way of representing this box so that I can encompass the entire noise inside the box without affecting the representation of the circuit. Okay, so essentially what I'm trying to see is that what should be inside the box so that the total output noise remains unchanged, right? So what should be inside the box? That's the goal. Okay, so given that the goal is established, let's see. So let's say I have this noise source, and I understand that I'm interested in the output short circuit current. Okay, and I want to represent this as just like in case of a resistor, we are able to represent the resistor output as a voltage source in series or a current source in parallel. I would like to ensure that and a noiseless resistor. I would like to ensure that I have something. I like to ensure that I have a what should I put here so that I have a noiseless transistor, but yet I have the same output noise current, which means that all the noise sources have to be translated here, right? Or must contain, or not all, must contain noise voltage / current sources such that I out noise is unchanged, right? Okay, so that's the goal. Okay, so now again must understand that we are trying to drive this circuit with some RS and some VI, which means I have the same VI and RS. And whatever inside the block we have should not be a function of RS and VI, right? So this should be a, again, another thing is the equivalent sources must be independent of RS or VI. Okay, so these are the two criteria. So we have to honor, right? Because we are trying to model the noisy network, and so that I should be able to drive this noisy network with any VI or RS. Okay, so if the stuff inside the box is a function of RS, that defeats the purpose. Okay, fine. So let's start simply. So as it turns out, there is a long-winded proof to come to arrive at this equivalent network. We'll not get into the long-winded proof. I'll give you a intuitive, borderline hand-wavy explanation of why it is so, and hopefully it will make sense, right? Okay, so let's do that. So for the time being, let's say, by the way, an important consideration that we will consider in this case is the input impedance of the transistor is not infinite. It has a capacitive impedance, so we'll consider the capacitive impedance. This capacitor CGS is there. This is what we are going to consider. So now, because the CGS is inherent to the transistor, we cannot take it out. So we will have to put something before that, right? So what is it that we can put so that in the presence of, let me put this RS also. I am not including the VI in this model because ultimately VI is a signal source, and the noise source can be tackled using superposition. So I am just not using I am desensitizing the signal source. I am keeping the RS. Okay. So if you recall, in case of a resistor, we could replace the noisy resistor with a noiseless resistor and a voltage source in series. So in this case, we would like to replace the noisy transistor with a noiseless transistor and a voltage source. Correct? So let's do that. So if I replace this guy with a noisy transistor and a noise, by the way, can I replace this with a, let's say, a voltage source V in, so I call this Vn in, that is input referred voltage source. If I do this, what do I get? So if let's say I model the input, so let's say case 1. So I model the by noisy transistor as a noiseless transistor and a voltage source, just like I have shown here. I can obviously do that, but the issue is then I'll not be able to use this model to drive an input, because this input port, the input port will not allow, this model will not allow any input to be driven because I have a voltage source in parallel to it, right? So this cannot be used. So this model cannot be used. Okay. Can I use this guy? Then other option is to use a voltage source in series, say a noise voltage source in series. Can I use this? Looks like I can use this because I can still now drive some input. But let's consider a case in which uh, in which your uh, your RS is infinite, right? So what happens if RS is infinite? If RS is infinite, in this case, if RS tends to infinity, uh, what happens to the entire network, the equivalent network? The equivalent network becomes, okay. So what is the VGS here? Incremental VGS. There is clearly no current across the capacitor. So the incremental VGS is 0. So what is the incremental current at the output? Incremental current is 0. But is that a correct representation? Clearly not, because I have an output noise current, right? I have an output noise current regardless of whether the RS is infinite or not. Again, I would like to emphasize that this is an incremental model. I am not showing the the biasing transistor, the biasing equivalent, right? So it is assumed the transistor is biased. Incrementally, the input is open, right? If the incrementally the input is open, and if I model my input, the equivalent noise input, right, as the one that I have shown on the right, then clearly looks like if RS tends to infinity, we have a problem because it is not able to model the output noise. The output noise is going to 0. Why should a transistor care, right? Whether the RS is infinite or not, it has its noise and it should always come out. Okay, so this clearly seems to be a problem also. Uh, what about what about a what about the case where I have a, so this is case 2. It can partially work, right? It seems to be that I still can drive an input, but there is a problem of when RS tends to infinity. What about another case, right, where I use a current source to model it. So I use a current source to model it. Right, so let's say this is a current source. IN input referred. So can I use this? Obviously I cannot, just like case 1. In this case, if there is a current source that I am using, then the voltage across the VGS is always INP times j omega c, right? And it is independent of the input. So again, I will not be able to drive an input. So this also cannot be used. So this is case 3. Okay. What about the case in which I have a current source in parallel? So this is again IN input referred. Then you have a resistance here. Looks like again this seems to be a good option, right? Because I'll be still be able to drive an input. But what about the case in which RS is 0? If RS is 0, if rs, so firstly, if rs equal to infinity, does it work? So if rs equal to infinity, your vgs is equal to in by j omega cgs, which means there is a finite vgs and I am going to get some output current. So I out is then in by j omega cgs times gm, right? Which means that is si out is in input referred, right? Input referred, which means this will be sn input referred by omega square cgs squared times gm squared, right? And this essentially, I know that si out is 4 kt gamma gm, which is sni input referred by omega square cgs squared times gm squared. So my input referred noise current is essentially 4 kt gamma by gm times omega square cgs squared, right? So this seems to work, but what happens if rs equal to 0? So, but if rs equal to 0, your vgs is equal to 0, right? Your vgs equal to 0, so so essentially your I output current is again equal to 0, right? So this model does not work when rs equal to 0, and this model does not work when rs equal to infinity, right? But does this model work when rs equal to 0? So if in this case, if rs equal to 0, this reduces to this model, correct? Which essentially means that your vgs is equal to v in, right? So this is here this is vn input referred. So in this case, my vgs is equal to vn input referred, vn input, which means I out, so I am referring to this. I out is equal to gm times vn input referred, which means that our svn input referred is si out by gm squared, which is 4 kt gamma by gm, right? So looks like the voltage source in series condition works for when rs equal to 0, but does not work if rs equal to infinity. But the current source in parallel works for rs equal to infinity, but doesn't work with rs equal to 0, right? So, but the other two options doesn't work either way, right? So if these two conditions work individually for cases of rs equal to 0 and rs equal to infinity, then it makes sense probably to combine both of them so that they work in the presence of any rs, right? So if that seems to be the solution, then we can try it out. So let's try it out. So the proposal is, so this is rs, we let's say have a vn input referred, and we have a in input referred, and we have this guy, and this cgs is here. So clearly this is going to work for the cases when Vn is when Rs equal to 0, or even when Rs equal to infinity, that we have already established. But what about when Rs is equal to some finite, right? If Rs is equal to finite, in this particular case, your I out noise should be independent of Rs. Note that this statement is true for only this configuration, right? Because I mean your this is unilateral two port, right? So the output does not affect the input, right? And there is no direct feed through from the input to the output. It only has to it has to develop a voltage of VGS, and then some output will come out, right? So in this particular case, again, this is not a rigorous proof, but in this particular case, I out noise should be independent of Rs. If I can show that in this particular case it is independent of Rs, then we are done, correct? So let's do that. So what is VGS in this case? VGS will be equal to if Vn INP and Vn INM if both the I can use superposition, right? I can use this is a linear LTI circuit, right, in an incremental model. So I can use superposition. So if I only use Vn INP and I open Vn IN the current source, then your VGS essentially becomes Vn INP by Rs plus 1 by j omega CGS times 1 by j omega CGS. And if I use this IN as the only source and I desensitize Vn, then this becomes INP times parallel combination of Rs and CGS, that is Rs times 1 over j omega CGS by Rs plus 1 by j omega CGS, which essentially means this is Vn INP plus Rs times INP by 1 plus j omega Rs CGS. Okay. Vn INP plus Rs times INP. Okay, fine. Now, what is Vn INP? How do I know what is Vn INP? Right, because these are modeled values, right? These are modeled. These Vn and In at the input side, those sources do not exist. They are modeled sources, right? So what values of Vn INP and In INP should we have so that it satisfies this this requirement? So how do I find out Vn INP? So in order to find out Vn INP, I have to set up the circuit in such a way that the In INP does not affect my affect the total output, right? Now what can I do? I know that I've already established the fact that if Rs equal to 0, right, the effect of In INP does not come out, right? So to find Vn INP, then short Rs, right? If I short Rs, just like where did I go? So in this case, if I short Rs, then the current source will not be able to generate any VGS, right? If the current source is not able to generate any VGS, then the output current is 0. but the total current does not change. The total output current does not change, and that total output current, whatever I will get, will be because of VNINP only. So from there I'll be able to get the value of VNINP, right? So if I short RS, then my equivalent noise model then essentially becomes VNINP this, right? So this does not come into picture at all, because incrementally it's not, that current source is not able to generate any voltage across VGS. So I have only VNINP. The capacitor also does not play a role because VNINP comes in parallel to the capacitor. So again, like before, your IN out is GM times VNINP, right? Which means that your VNINP is IN out by GM, correct? So to again, now I have to find out INP, right? So to find input referred noise current, what do we need to do? We need to set up the circuit in such a way that VNINP does not contribute to any output current. So make RS to be infinity. So what happens? INP capacitor, okay. So VNINP does not play a role, only INP plays. So the voltage it develops, so VGS is essentially INP by J omega CGS. So output current is GM times VGS. So your essentially IN out is GM times INP by J omega CGS, which means that your INP is, so by the way, the current direction has to be taken into account in between both the cases, right? So your INP is IN out times J omega CGS over GM, right? So now let's plug in those values here of the VNINP and INP that we got. So your VGS, so in the total network VGS, which was VNINP plus RS times INP by 1 plus J omega RS CGS. And what is VNINP? It is basically IN out over GN. And what is INP? That is IN out times J omega CGS over GM. By the way, I probably have to make a correction here. I have not stayed true to the symbols. Should use IN out here. Okay, fine. By 1 plus J omega RS CGS. So if you see, if you take out IN out by GM, this becomes 1 plus J omega RS CGS by 1 plus J omega RS CGS. This goes off. So VGS is essentially IN out by GM, which means that your GM times VGS equal to IN out, which means that this satisfies, this means that the VN INP and INP model is consistent. Correct? So, to cut a long story short, what I essentially did was to say that if you have, I took the example of a transistor, but in general, if you have a two-port network, or so if you have a two-port network where you have an output port, let's say 2 dash, and you have an input port 1 dash, and you have noisy elements inside this two-port network, right? It's a linear LTI based two-port network, and with the noise sources inside, right? So you can model this two-port network, right? You can model this two-port network as a noiseless two-port with a contraption up front, and the contraption looks like a VN and an IN, and like this, right? And if you have to, now if you are somebody who is designing a block, let's say again I come back to that example that I am designing block 1, and this is my block 2 two-port, then what do I expect from the designer of block 2? I expect the input characteristics of block 2, but not only that, now I am expecting the equivalent noise model of the block 2, right? So when I am asking for a noise model, what I am essentially saying is that give me this characteristic of block 2, that is, what is the input impedance? If I say this is the Zin for block 2, and I would require the input referred voltage for the block 2, I would require the input referred current for block 2, and this is the model that I am going to use to design my block 1. Why is this important? Obviously, the Zin is important for block 2 because that helps me understand what should be the drive strength of block 1, right? So that is analog circuit 101. But the requirement of VN INP and VIN INP encapsulates the entire noise performance of the block 2 into 2. So generally, when I am teaching analog circuit courses, I would model. You would very commonly see models of input referred noise voltages and not the input referred noise current. In fact, if you see many instrumentation amplifier data sheets, you are going to see input referred noise voltage than input referred noise current, and they are not wrong. And the reason those are more effective is because at lower frequencies, generally at lower frequencies, the Zin is almost infinite, right? And your RS is basically Zin is much more than RS, right? If you assume Zin to be infinite and RS to be much smaller, right? So essentially you can assume that it's a case, equivalent case is RS equal to 0. If RS equal to 0, when you put RS equal to 0 in this model, right, you see that the effect of IN goes off, right? So in many instrumentation amplifiers, for example, when you are doing input referred noise model, you only see VN INP. But when you go to higher frequencies where nothing is really open and nothing is really short, right, as we have talked about in the previous lectures. So very often you would require the effect of both of these together. And before we stop this lecture, an important caveat to understand is that obviously VNINP and ININP are correlated, right? So note that VNINP and ININP are correlated. They are not uncorrelated, right? Because they are correlated, when we do noise analysis, ideally we should not be treating them separately and add their powers up as we used to do earlier. We should be using them in together, just like we did it here, right? For example, here we, in this step, right, in this step we use them together, and we did not simply square them up and added their powers, correct? So whenever you have correlated sources, then you'll have to deal with them with proper signs in voltage domain, right, and arrive at the final output, and then whatever the final output is, and then you square and do whatever you want to get the final noise. But at this stage you need not. Okay. So the other part that I must mention is that why is, even though it should be evident by now, why is VNINP and ININP correlated? They're simply correlated. If you go by the example that we took, both of them are essentially modeling the noise from the same transistor. So the source is essentially the same that they are trying to model. So if they are modeling the same thing, they obviously have to be correlated, right? Okay, fine. We'll stop here and we'll continue with some more amount of noise in the next class.